Tangents and tangent planes. If we have a two-dimensional function, a function y is equal to fx, which we plot in a two-dimensional space, then looking at the tangents, it's a line which is giving us the direction at each point. I have a function and a tangent to it at some particular point. Now, suppose I will change the position of this point, then what will happen to the tangent? Then the slope of the tangent is changing at each point. This is with the function, a cubic function I have taken and its derivative I have calculated. Then the slope and the equation of the tangent we can find because it's a straight line passing through that point, and its slope is given by the derivative of that function, provided the function is differentiable. Suppose the same concept is to be taken to a three-dimensional space. Now, instead of a function, we have a surface, and instead of a tangent line, we will have a tangent plane. Let's see how this same thing works in a three-dimensional space. Here I have a three-dimensional curve which is of quadratic form, upward parabola. This is my three-dimensional function. A two-dimensional it's actually a surface which we can visualize in a three-dimensional space. So it's taking points from the plane, from the xy plane, and it's taking these points to the three-dimensional space. Now, if we want to calculate the slope, as the concept of slope in a three-dimensional space, we will be doing that with the help of a tangent plane. So how do we know, how do we find the tangent plane? That's with the help of a gradient to a surface. I have calculated the gradient to this surface and I am plotting that. If if we change the point, let's see how the tangent plane changes. So it's giving us the direction at each point. Now our plane will be having direction with respect to x, with respect to y, and with respect to the z axis. So it's not a single line right now. It will be a plane, a three-dimensional plane. So this is how the concept of function tangent to a surface and tangent plane, and the same thing can be generalized to higher dimensional spaces. But it's when we go beyond three-dimensional space, we lose the geometry. But the concepts are same. From one-dimensional to two-dimensional to three-dimensional, the concepts remain same. There is no change in the analogy between the spaces. Only we, because of the our limitations of the how we visualize a four-dimensional, five-dimensional spaces, we won't be able to see them, but we will be able to perform calculations as we do in usual three-dimensional spaces. This is how the tangent planes move to this around this surface. These are very important in the context of multivariable calculus and optimization techniques. So usually our optimization problem is formed in such a way that our surface is a convex surface, and that convex surface we have to look at the minima of that surface or the maxima of that surface, and that's usually at the bottom of that surface if there's a convex or concave. Now at that point the tangent plane becomes flat. Let's see how that goes. If we take our tangent plane to 0 0, we look at the slope of this tangent or the direction ratios of this tangent plane, and we see that it becomes flat. Now this is what helps us in optimization techniques. So this is one of the ways we do the optimization is for obtaining the maxima minima of that function with the help of gradient or the derivatives in higher dimensional space.